In statistical mechanics. Today we are going to start a new chapter of ensembles. Actually, ensemble theory is a very important theory of statistical mechanics. Why it is very important? Can you say? Actually, you have seen earlier that when you study statistical mechanics, then always you talk about the average value or the probable value of an observable, because when we deal with a statistical system, the exact value of an observable uh, is cannot be said exactly. So we always talk about the probable value or the average value. And that's why a famous physicist which has done enormous work in the field of statistical physics named W Gibbs introduced the concept of ensemble in statistical mechanics. Actually, introducing this concept of ensemble in statistical mechanics, the prime aim of Gibbs was what? His prime aim was to calculate the average value of the physical quantities, or you can say observables. So, in a very small sentence, you can say that the concept of ensemble was introduced in statistical mechanics by W Gibbs, and the purpose of introducing this ensemble theory was primarily calculation of the average value of physical quantities. Okay. Now, this is the first lecture of myself on this subject. So actually in this lecture we will just see an overview, an outline of the ensembles in statistical mechanics. But after this lecture we will start to deal with separately the different three types of ensembles in statistical mechanics in very detail. But here I am going to introduce you the different type of ensembles. Actually, when you consider that there is a collection of particles, okay, then in that collection of particles, a single particle is called a system. Okay, in other branches of physics, system means collection of particles, but here a particular particle is called system in case of collection of particles. Okay. And when you consider a collection of such type of systems, that collection of systems or that collection of particles, you can say, that is called assembly. So assembly is what? Assembly is the collection of systems, and system is what? System is simply particle. Okay. And the collection of a large number of assemblies is called an ensemble. Okay. So I have mentioned it here. You can see that collection of a large number of assemblies is called an ensemble. Okay. So what you have learned? You have learned that in case of a collection of particles, a single particle is called a system, and collection of such systems is called assembly, and a collection of assemblies is called an ensemble. Okay, this is just a brief idea or just a brief concept regarding this ensemble. Okay, actually all the members of an ensemble which are identical in some feature like volume V, energy E, and number of particles N are referred to as elements of the ensemble. These are called elements. Actually, these elements are macroscopically identical but microscopically different. Okay, and in fact the elements being imaginary do not interact with one another and behave independently. Okay, so you can say that if we consider an ensemble and we divide this ensemble in different parts having the similar property like volume, energy and number of particles, then those parts of the ensemble are called elements of the ensemble. And these ensembles are actually imaginary. This is just a mental thing, or you consider the mental copies of different parts of this ensemble. Okay, and so we simply say that all the ensembles have same macroscopic properties, so we simply say that they are macroscopically identical. But when you talk about these elements on microscopic level, on atomic or molecular level, then you will see that they are different. Okay, and there is a very important assumption that we always consider that these elements do not interact with one another. Okay, so after getting these ideas, if you want to define this ensemble in a single sentence, then what will be the complete definition of this ensemble in just a one sentence? You can see that we define that an ensemble is a collection of large number of essentially independent and non-interacting assemblies with same Hamiltonian. This is the a remarkable fact that you can define ensemble as a collection of large number of assemblies, and that assemblies must be independent from one another and they also should be non-interacting. Actually, when you say non-interacting, the assemblies are non-interacting, what does it mean? It means when you will try to find out or try to calculate the eigenstate of an assembly, you should not consider its interaction with the neighboring assemblies. So taking each and every assembly independent from others, we calculate its eigenstate, and that's why we simply say that these assemblies are non-interacting. Okay, I think you are getting the things. Actually, in an ensemble, you can see the system plays the same role as the non-interacting molecules do in a gas. The macroscopic identity of the systems constituting an assembly can be achieved by choosing the same values of some set of macroscopic parameters like volume, energy, number of particles or chemical potential. Actually, these parameters uniquely determine the equilibrium state of the system, and so in accordance with these facts, the three types of ensembles are widely used. But never think that ensembles will be actually of three types. The ensembles may be of infinite types, but among those large number of ensembles, the widely used or the most important ensembles are what? The most widely used and most important ensembles are micro-canonical ensemble, canonical ensemble and grand canonical ensemble. Actually, all these three ensembles we will deal in the forthcoming lectures separately in very detail. First of all, you will look upon the ideas of micro-canonical ensemble, after that canonical ensemble, and finally we will deal with the grand canonical ensemble. But as I have told you earlier, that the basic aim of this first lecture on ensemble theory is only to introduce you all these ensembles. in a qualitative manner without any calculation. You have to remember some of the important features of these ensembles. Okay? So let us start to know about the basic facts or the basic features of the first ensemble which I have mentioned here, which is microcanonical ensemble. Okay? When you talk about the microcanonical ensemble, what are its basic features? Actually, the microcanonical ensemble is a collection of essentially independent assemblies having the same energy E, same volume V, and the same number of particles N. Okay? And all these systems are of the same type. Okay? All these systems are of same type. Actually, symbolically, I have shown in this figure this microcanonical ensemble. Here the parameters E, V and N have been shown, and you can see that the values of E, V and N, that is energy, volume and N, are same for all assemblies. Okay? But let us think how this energy can be same for all assemblies. Energy will remain conserved, or energy will remain constant for every part only when there is no exchange of energy. So the assemblies must be enclosed in an enclosure having non-conducting walls, because if you will take the assembly inside a container whose walls are conducting, then there will be an exchange of energy. Okay? But here there should be no exchange of energy, and for that the wall of the container must be non-conducting. Okay? Or you can say thermally insulated. Okay? So the requirement that E remains constant, that demands that the walls should be what? Walls should be non-conducting, or you can say thermally insulated. Okay? Again, another condition is what? V should be constant when the volume will remain constant. If the walls of the enclosure is rigid, if it is non-rigid, the volume may increase or decrease. So walls must be rigid to keep the volume constant. And if you say that number of particles should also remain constant, for that purpose the wall should be impermeable. It means the particles should not exchange between the two assemblies. There will be no exchange of particles. So in this case you can say that our assembly is isolated, because energy of an isolated system remains constant. So in brief, I have mentioned it here. You can see that assemblies are isolated, separated by rigid, impermeable and thermally insulated walls. And it means this impermeable condition requires for keeping this N constant, impermeable. Okay? So this is the basic fact. Actually, this is a very important objective question of your examination. Always such type of objective question in your examination is asked, that in case of microcanonical ensemble, what is the set of parameters or quantities which remain constant? You should say that these are E, V and N. Okay? Now, when we consider a closed system for which the Hamiltonian H which is equal to E is equal to constant. Okay, energy remains constant. Actually, the locus of all the phase points in phase space having equal energy is called energy surface. Actually, you can see this figure. I have shown here two energy surfaces. Actually, this curved line is not a line, but imagine that this is a surface, and at all points on this surface energy is equal to E. Similarly, we draw another surface close to this E, and energy at any point of this another surface is E plus delta E. So these two surfaces are called energy surfaces or ergodic surface. Okay. In fact, the density of phase point between these two ergodic surfaces or energy surface remains constant. But outside of these two surfaces, that density distribution function will be 0. So you can say that if we consider the two ergodic surfaces having energy E and E plus delta E, then the number of phase point between them is constant, which I have mentioned it here. You can see rho equal to constant. And outside of these two surfaces, this density distribution function is 0. Actually, in this condition, a very useful ensemble can be obtained by taking the density as equal to 0 for all values of the energy except in this region, that is energy between E and E plus delta E. Okay. And so you can say that an ensemble is specified by the density distribution function rho equal to constant between energy E and E plus delta E and 0 outside of this range. That ensemble is called microcanonical ensemble. Okay, that is called microcanonical ensemble. And as you know that rho, which is density distribution function, is a function of energy. Okay, and as energy is here constant in this ensemble, so you can say that rho being a function of energy, this ensemble is in a statistical equilibrium. Okay, and the average properties predicted by such ensemble will not vary in time as the ensemble is in a statistical equilibrium. Okay, again you can say since rho is constant within the energy cell, the distribution of phase point is uniform in accordance with the Liouville's theorem. Okay, so these are the basic features of I have not mentioned all those facts which I have just explained, so you can pause the video and write down all the facts in your notebook. Now actually in this case the partition function is simply equal to delta gamma, which actually represents the hypervolume in phase space. So hypervolume in phase space is taken as the partition function in case of microcanonical ensemble. Okay, so I hope you have definitely understand the all important features without any rigorous calculation. I am just dealing the facts in a qualitative manner, but after this lecture you will see again these things in very detail by mathematical calculation. Okay, now we will talk about the second ensemble, which is called canonical ensemble. Okay, actually this canonical ensemble is a collection of essentially independent assemblies having the same temperature T, volume V and number of particles N. Okay, now think that how this T, V and N will remain constant. You know that for keeping T constant, there must be an exchange of energy. Let us consider that there are two assemblies in contact of one another, okay, and there is an exchange of energy between them. The exchange of energy will take place until temperature of both the assemblies will become same. So for keeping T same, there must be an exchange of energy, and that's why here we do not consider energy as the parameter. Okay. Another way of keeping this temperature constant will be what? Let us consider that there is a hot reservoir at a very high temperature T, and all the assemblies are in contact of this hot reservoir. Actually, symbolically, this is your reservoir, let us say R, and these are assemblies which I am marking by the symbol A. So when you will make a contact between the heat reservoir and the different assemblies, all assemblies will become at a temperature T. So in this case, assemblies are in thermal contact with a large heat reservoir or with each other. Okay. And due to this, T remains constant. Now, when the V will remain constant, you have just seen, if you want to keep the value of V constant, you must keep the assemblies inside an enclosure having rigid wall. Only then V will remain constant. And for keeping N equal to constant, the wall of the enclosure must be impermeable. There should be no exchange of particle. Okay. So in this case, there will be an exchange of energy. There will be an exchange of energy, or you can say energy fluctuation will take place in case of canonical ensemble. Okay. But temperature of all assemblies will be same, volume of all assemblies will be same, and number of particles of all assemblies will be same. And for keeping T constant, either the different assemblies should be in contact of one another, or all the assemblies should be in contact with a heat reservoir. Okay. For keeping V constant, the walls of the container should be rigid, and for N to be constant, the wall should be non-permeable or impermeable. It means such wall will not allow the exchange of particle. Okay. So I have mentioned here that assemblies are separated by rigid, impermeable and dithermic walls. Dithermic wall, because there should be an exchange of energy, and for that the wall should be conducting, then energy will be exchanged. So in this case, wall is not non-conducting or insulating, but it is dithermic. Okay. And exchange of energy leaves the temperature T same. Now in this case, how the density distribution function will be defined, I have mentioned this result here directly, but when we will discuss this canonical ensemble separately, then we will derive this formula. But here I have directly mentioned it, that the density distribution function, or you can say the Gibbs density distribution function or probability distribution function, which we have learnt earlier. In this case of canonical ensemble, it is given by rho of QP. Here Q is the position coordinate, you know, and P is the momentum coordinate. And this is given as a constant A times A e to the power minus E by KT. Okay. As I have told you, this expression has been directly written here, but we will see the proof or derivation of this formula in the forthcoming lecture on canonical ensemble. So in this case, you can see that this density distribution function actually exponentially decreases with energy if you keep the temperature constant. So if you will plot a graph, let us say, of this rho in against of energy E, you can see when energy E is 0, then this rho will be maximum and this will be equal to A. And with increase in E, the density distribution function will decrease exponentially. Okay? And in this case, partition function is denoted by the symbol Zn, and this is given by integral of e to the power minus e by kt d gamma. D gamma, you know, this is elementary volume in phase space. And this result has been also mentioned here directly. Because in your university examination, there is a very important question frequently asked to you, that give an overview of ensemble theory. When such a question will be asked, you have to write the main feature of all these three ensembles. So no derivation will be required, and you have only to mention the important facts. So all these results has been written here directly, without any discussion, without any calculation, without any derivation. So remember it. And there is another question too. What are the main differences between three ensembles? Then in a tabular form you can mention all these properties. Okay? But don't think that I will not explain these facts in detail. In forthcoming lecture, as I have told you, all these formulas will be completely derived by rigorous method. Okay? So after getting the idea of canonical ensemble, now we will see the main feature of the third ensemble, which is called grand canonical ensemble. Actually, we will see later on that this grand canonical ensemble is just a combination of the canonical ensemble and micro-canonical ensemble. Actually, in this case, energy is not constant. It means there will be an exchange of energy between the assemblies. Okay? There will be an exchange of energy. And the number of particles also does not remain constant. It means there will be also an exchange of particle between the among the ensembles. Okay? And for this, for exchange of energy, walls should be dithermic. Okay? And for exchange of particle, the wall should be permeable. But in this case too, V remains constant. And for keeping volume constant, the walls must be rigid. Okay? Walls must be rigid. So in this case, you can say that in case of grand canonical ensemble, assemblies are separated by rigid, permeable and dithermic walls. Okay? This condition of rigidity maintains the condition V equal to constant. Permeable means exchange of particles is allowed, and dithermic means exchange of energy is allowed. So in this case, you can say there will be two types of there will be two fluctuations. We will calculate in the forthcoming lecture energy fluctuation and this number of particle fluctuation in case of grand canonical ensemble. Okay? But what are the three parameters which will remain same for all the assemblies? In this case, actually, due to exchange of energy, temperature remains same. Volume is same because walls of the enclosure is rigid. Okay? And due to the exchange of particle, the chemical potential of different assemblies will be also same. So the set of three parameters which are same for all assemblies in case of grand canonical ensemble are what? They are T, V and mu. Mu actually represents the chemical potential. If you have not a complete knowledge of chemical potential, I will suggest you go through my videos on chemical potential in the playlist of my channel named Thermodynamics or Thermal Physics. There you will get a detailed discussion of chemical potential. So when you will see this video and you have confusion what is this chemical potential, must watch my video on chemical potential in the playlist of thermal physics. Okay, and as I have told you that in this case exchange of energy and particles both take place, so there will be energy fluctuation and number density fluctuation in this case. Now the density distribution function in this case is given by this expression, which I have again just mentioned directly without derivation. You will see the derivation later on. Rho of Qp equal to A e to the power mu n minus E over kT, where you know mu is the chemical potential. And actually in this case the partition function is given by this expression. This is the product of summation over n e to the power mu n by kT times Zn. This Zn is actually the partition function for canonical ensemble. So when you will multiply the partition function of canonical ensemble, which is denoted by Zn, by the factor summation over n e to the power mu n by kT, then you will get the partition function for this ensemble. Okay, so these are the basic features of three types of ensembles, and you should remember these things. And when in your examination, particularly in university examination, a question is asked, write down an essay on ensemble theory or give an overview of ensemble theory, okay, then you should write the answer in this format. Okay, actually the three mentioned ensembles are only examples of infinite number of ensembles that can be considered. As I have told you earlier, don't think that there are only three types of ensembles. There are infinite types of ensembles. Among those, these three are very important. Okay, actually these three are particularly useful for two main regions. What are the two important regions that we consider these three ensembles? Firstly, you can say that they correspond approximately to the types of thermodynamic measurements most frequently made in practice. And secondly, you can say that in large assemblies it is useful to find that the values of thermodynamic quantities are not very sensitive to the method of measurement. Okay, so I hope you have now a brief idea, just an outline of all these three ensembles. But as I have told you, in the forthcoming lecture we will first of all start to study microcanonical ensemble in detail, and then step by step in different videos we will see the concept of canonical and grand canonical ensembles. Okay, thank you very much.